Hi, I'm Tom Biebighauser with Wetland Restoration and Training. Years ago, it was common to build dams across the stream outlets of lakes to make them larger and deeper. Today, we understand how these dams can affect aquatic organism passage and require regular and expensive maintenance. I'd like to show you how we removed a dam and restored a lake in British Columbia, Canada. Let's get started. Violin Lake is a natural lake located in British Columbia near the border with the United States. Goodeve Creek is a natural outlet for Violin Lake that flows south into the United States. The stream is a series of beaver ponds where you don't see a deep and a narrow channel with defined bed and banks. This is how most of the streams and valleys appeared historically before beaver and their dams were removed and the forests were cleared and ditches were dug to create farmland. A narrow earthen dam was built across Goodeve Creek at the south end of Violin Lake in 1918. The dam was built 3.7 meters high and 48.8 meters long, and this was done to increase the depth and the size of Violin Lake to 24 hectares. Violin Lake was modified so it could serve as a water supply to the city of Trail in British Columbia, Canada. Violin Lake and the nearby Cambridge Creek Reservoir were the primary sources of water for the city of Trail from 1918 to 1994. The Violin Lake Dam was rebuilt in 1953. The rebuilt dam allowed Violin Lake to store an additional 558,000 cubic meters of water, which equals approximately 147,408,000 U.S. gallons. The dam increased the depth of the lake from 21.5 to 23 meters and expanded the surface area of water by about 2.66 hectares. Prior to the reconstruction of the Violin Lake Dam in 1953, there was a large and shallow bay containing many fallen trees at the south end of the lake. These photographs show that reconstruction of the Violin Lake Dam was carried out during the winter, a time of year when proper soil compaction is extremely difficult because the ground is frozen and saturated. A mixture of soil and rock was hauled into the site by dump truck and used to build the dam, rather than using soil that is high in clay and compacted under suitable conditions. This photo shows a mixture of soil and rocks being placed over downed trees to build the dam. I have found that dams built from coarse texture soil that is placed over wood will leak. The dam was not built with a concrete or a clay core in the center to prevent leaking. The dam was armored with rock in places so that wave action would not cause damage to the dam and to help protect it from muskrat and beaver burrowing activity. An emergency spillway was built to carry overflow from Violin Lake into Goodeve Creek. The spillway was 11 meters long and 2.4 meters wide. The spillway was made of wood and concrete. Here you can see water flowing both in and under the spillway. The head cut located at the outlet of the spillway is washing soil from under the spillway, which is a major cause of dam failure. Beavers had blocked the entrance to the emergency spillway. If the beaver dam is not removed, water flowing over the Violin Lake Dam could bypass the spillway and erode the dam, potentially leading to a washout. The nearby Cambridge Creek Reservoir Dam was rebuilt in 1967. Cambridge Creek flows north into the Columbia River. A natural ridge separates the watershed of Cambridge Creek with that of Violin Lake. To move water from Violin Lake into Cambridge Creek Reservoir, the City of Trail installed a piping system to siphon water from Violin Lake across the height of land and into Cambridge Creek. The original siphon pipes were made using beveled strips of wood we call staves, and these were bound tightly together with steel wire. Pipes were commonly made using wood staves or clay tiles before plastic was invented. In 1953, the wood stave pipe was replaced with the current 880-meter-long, 400-millimeter diameter transite pipe, which was made using asbestos and cement. Installation of the siphon pipe for moving water from Violin Lake into Cambridge Creek Reservoir was a major project. It was necessary to dig a deep trench through rock and soil and to shore up the sides of the trench with timber so it would not collapse and injure the workers. The large and heavy pipes made from concrete and asbestos had to be lowered into the trench without breaking them or crushing the workers below. I can't imagine how wet and cold the workers were by the end of the day. The presence of the wooden frame illustrates how dangerous it was to work in the trench. The frame formed a protective cage designed to prevent workers from being crushed if the sides of the trench collapsed. Here's where they dug out the north bay of Violin Lake and drove in pilings to construct a cofferdam, which is a temporary watertight enclosure. It's built to keep water out of an excavation so they could install the inlet to the siphon pipe. This early crane is being used to place the large and heavy siphon pipes into position. The individual in the center of this photograph is wearing a deep diving suit. Just think of the strength and courage it took to fit the siphon pipes together underwater. Robin Anschild is standing on the banks of the trench dug for the siphon 68 years after the pipe was installed. The trench filled with water. The siphon pipe is buried deep in the ground beneath the water in the trench. Large trees are growing on the soil piled along the edge of the trench. This building contains the valve that opens and closes the flow of water in the siphon pipe. This photo shows a much smaller dam called the Violin Lake North Dam that was built to prevent water from flowing on top of the siphon pipe into Cambridge Creek from Violin Lake. This map shows the complex system of pipes, ditches, and dams used to move water from Violin Lake into Cambridge Creek. Gates have been in place for years with signs alerting users that the area surrounding Violin Lake and the Cambridge Creek Reservoir were closed to public motor vehicle use. This map shows the infrastructure that was in place for providing drinking water to the city of Trail. In 1994, the city of Trail changed its water source from the Cambridge Creek Reservoir and Violin Lake to the Columbia River. The city of Trail stopped using water from the Cambridge Creek Reservoir system due to concerns about water quality. Both the Violin Lake Dam and the Cambridge Creek Dam, they required constant monitoring and frequent maintenance, even though they were no longer being used for water supply. Beavers often blocked the emergency spillways of the dams with branches, trees, and soil that had to be removed. The dams could fail with runoff from one major storm if the spillways were blocked. The BC Dam Safety Consequence Classification rating for the Violin Lake Dam was significant. The risks associated with failure were determined after modeling various hydraulic scenarios. The spillway for the Violin Lake South Dam needed repair. The city of Trail determined that the cost of continued operation and maintenance of the dams outweighed the benefits and decided to remove the dams and restore the area's natural lake, wetlands, and streams. The British Columbia Wildlife Federation worked in partnership with the City of Trail to design, plan, and implement the removal of the Cambridge Creek Reservoir and the Violin Lake Dam. Obtaining the permits required by the provincial and federal government prior to implementation of the project was complicated, expensive, and time-consuming. The project would not have been possible without the help and encouragement of John Howes, engineering technician for the City of Trail. The funding needed to implement the project was received from the British Columbia Healthy Watersheds Initiative Program, Investing in Canada Infrastructure Program, and the City of Trail. Episode 31 shows how we removed the Cambridge Creek Reservoir Dam and restored wetlands, streams, and forests in the Cambridge Creek Valley. In 2020, we began lowering the elevation of water in Violin Lake by opening the valve on the siphon pipe. Water from Violin Lake flowed out of the siphon pipe into Cambridge Creek and then into the Cambridge Creek Reservoir. The water level in Violin Lake was drained low enough so that the dam could be removed without water flowing over the construction site into Goodeve Creek. This was important because of the high cost and the effort associated with pumping water around a dam while it's being removed. We worked to identify the historic elevation of the valley before the dam was built by taking elevation readings where the stumps of trees that had been inundated for years were now exposed near the inside base of the dam. The presence of tree stumps in the drained bay that was adjacent to the dam showed us that the soil had not been removed from the lake basin to build the dam. We also took elevation readings on the ground immediately downstream of the dam in areas that had not been disturbed when the dam was built. We drove a stake in the ground to serve as a benchmark for construction. The elevation on top of the stake would be the same elevation in which Goodeve Creek would begin flowing over the dam after it was removed. To determine the slope of the restored section of Goodeve Creek after the dam was removed, we calculated the percent slope between the point where the stream would begin flowing across the former dam and the point where it would end by tying back into the natural channel. The restored section of stream would flow into a beaver pond downhill of the dam after it was removed. Robin Anchild, Miranda Cross, and I prepared the designs for the restoration of the Goodeve Creek where it would flow over the former dam location. Our designs were reviewed and approved by an engineer. The orange hatched areas on this drawing shows where the soil in the dam would be placed. The artificial channel that had been created for the spillway would be filled in with soil. The stream would be restored on a 2.1% slope with the channel and floodplain being armored with rock. Topsoil would be spread over the restored floodplain, but not in the restored stream channel to control erosion. A floodplain that was level in cross-section and 10 meters wide would be built. A shallow stream channel averaging 2.5 meters wide would be built on the floodplain. The floodplain and stream channel would be armored with a thick layer of rock that would control erosion and prevent beaver from digging a canal that could lower the elevation of water in Violin Lake. A buried vertical grade control structure made out of large rock would be built at the downstream end of the restored stream, and this is where water flows into the beaver pond. The structure would protect Violin Lake from head cuts that may occur downstream in Goodeve Creek should the beaver dams fail or are removed. Following the lowering of the water level in Violin Lake, we observed unauthorized dirt bike use on the exposed mudflats that were created as the lake receded. Individuals were driving through wetlands along the shore of Violin Lake. Motor vehicles were crushing juvenile western toads, which is a species at risk, and accelerating erosion along the shoreline. Tire ruts formed shallow ditches that drained areas which were wetlands prior to inundation, further degrading habitat. Our observations demonstrated the need to take action to protect vulnerable wildlife and to restore wetlands that had been submerged for many years while Violin Lake was managed as a reservoir. Our group selected Sublatis Environmental from Calgary, Alberta to provide heavy equipment with skilled operators to complete the Cambridge Creek and Violin Lake ecosystem restoration project. To make the greatest use of funding, we paid Sublatis hourly for each piece of heavy equipment with an operator while they were doing productive work. Robin Anchild or I were on site every day working with heavy equipment operators to restore Violin Lake. The narrow mountain road leading to Violin Lake was rough, and it had wet areas where our vehicles could get stuck. The first step we took in construction was to improve the road so we could access Violin Lake without damaging our vehicles. The excavator and dozer operators removed trees and boulders, graded the road surface, and applied gravel so that large trucks could haul rock and wood slash to our work site. We opened the siphon valve as needed to lower the elevation of water in Violin Lake so that Goodeve Creek would not flow over the area while the dam was being removed. Construction began with excavators removing and salvaging the rock that had been used to armor sections of the dam. The rock was placed in piles for later use in armoring the restored stream channel and the floodplain. We also used dump trucks to haul additional rock from the Cambridge Creek Dam that was being removed to the Violin Lake Dam site to use in armoring the stream and the floodplain of Goodeve Creek. We were careful not to damage this old-growth western red cedar tree that was growing near the dam during construction. The red arrow points to where the excavator has begun removing the dam at Violin Lake. Trees and shrubs are removed from the dam and placed in a pile. This woody debris will be spread after the stream and the floodplain are built. The excavator removes soil from the dam and places the soil where the dozer can spread it on the side of the valley. We frequently take elevation readings with the laser level to determine how much soil to remove. While removing the dam, we noticed an old road bed along the shore of Violin Lake that had been flooded by the dam. The red dashed lines show the approximate location of the old road. The old road was not visible when the water level in the lake was high. We agreed that the old road bed would be an excellent place to spread much of the soil that would be removed from the dam. Here's the old road after we covered it with soil removed from the dam. It still looks like a road. The excavator begins shaping the soil so it will look like a natural shoreline. We excavate shallow water wetlands along the edge of the old road, place logs and snags, and shape a gradual slope along the shoreline. Here's where the shoreline was restored from the old road. This is where the old road was located after the dam was removed. The hillside in the foreground that's covered with wood slash is where soil from the dam was used to fill and to naturalize the wood and concrete emergency spillway. The operator excavates the floodplain for the stream after the dam has been removed. Here's where we plan to dig a trench to build a buried vertical grade control structure. It's located where the restored stream would enter the beaver pond. While digging the trench, we uncovered topsoil, roots, and branches under the dam. This showed that the dam had been built on a permeable foundation and without a clay or concrete core that would have controlled seepage. We're using these large rocks to fill the trench to build the buried vertical grade control structure. I take elevations with a dual-sided grade rod and a laser level to see if the top of the boulders is too high or too low. The excavator now places a thick layer of rock that will span the width and the length of the floodplain for the restored section of Goodeve Creek. The rock used to armor the channel and floodplain were transported by dump truck from the Cambridge Creek Reservoir Dam we removed. Rock is pushed into the ground using the bucket on the machine. Soil is mixed with rock so plants can grow. The excavator is armoring the floodplain with rock that's pushed into the ground. It was not possible to dig a narrow channel for the stream because much of the floodplain was based on bedrock. The rock armoring extends up the sides of the valley and on either side to control erosion should beaver build a dam across the valley at this point. One can see the 2.1% slope being built for the stream and the floodplain of Goodeve Creek. This is the constructed floodplain for Goodeve Creek where the stream will flow over the dam that's been removed. We were allowed to spread woody debris over the sides of the valley, but not in the restored channel or floodplain to reduce the possibility of erosion. There is so much rock pounded into the ground, there is no way a beaver could dig a canal in the stream. Wetlands of various sizes and depths were built in the south bay of Violin Lake near where the dam was removed. These filled primarily with groundwater. The wetland basins were built with pits, mounds, woody debris, and snags to increase plant and animal diversity and to discourage use by off-highway vehicles. Wood slash was placed to protect the banks and the channel of the restored stream from being damaged by motor vehicles. The soil placed in the old road along the shore was loosened using the rough and loosen technique, and this included pits and mounds so that water would soak into the ground and plants could germinate and grow. Part of the project involved rebuilding a short section of trail across the restored floodplain of Goodeve Creek. We placed an abundance of rocks and wood slash on either side to encourage users to stay on the trail. Here you can see the new trail that was built with the excavator. Rock and wood were spread on the downhill slope to encourage people to stay on the trail. These hikers are using the trail to cross Goodeve Creek 2 years after the dam was removed. This is where the trail leaves the end of the Violin Lake Road. We carefully placed and embedded these boulders into the ground so the opening would be wide enough for people to pass, but too narrow for wider motor vehicles. When I later visited the site, it looked like someone had used a sledgehammer to break off pieces of rock to widen the opening. Our next action was to control erosion and to improve habitat along the shoreline of Violin Lake, focusing on the narrow zone between the Violin Lake Road and the lake. People had started driving their vehicles along the shoreline that was exposed when the water level in the lake was lowered to remove the dam. They were doing this even though the area was closed to public motor vehicle use. There were deep tire ruts in the shoreline in most places where trees had not fallen. The exposed shoreline was fragile and subject to erosion. Here's where a section of the Violin Lake Road was located before the dam was built. This is an area where soil was placed in the lake, possibly to create a campsite or a boat ramp. Here's where soil was used to fill an area of Violin Lake. These areas were obvious because they were being used for parking and were growing little vegetation. Here the dozer is removing soil that was placed in Violin Lake. The dozer operator works to remove soil fill that was placed in the lake and to restore the natural contours of the shoreline. When topsoil was exposed, we knew that the fill had been removed. The excavator loosens the soil and the area is reshaped by the dozer. Logs and branches are spread over the shoreline. Snags are placed to improve habitat and to discourage motor vehicle use. Here the excavator places woody debris to protect the ground from erosion and from being damaged by motor vehicles. We try to place the wood so it appears like it washed in during a major storm. No digging was done on this stretch of shoreline. The wood slash was hauled in by trucks from a ski run that was being built in the nearby town of Roseland. This shoreline has been protected by woody debris placed on the surface where digging was not allowed. Here's a steeper section of shoreline that's protected by wood slash that was placed by the excavator. Here is where we removed a section of the old Violin Lake Road that was being built along the shore of the lake. We made small wetland pools where digging was allowed. The small pools were designed to provide breeding habitat for frogs and toads. Andrew Steen is showing us a section of shoreline he restored using the excavator. The north end of Violin Lake was heavily damaged by people using unauthorized campsites and by vehicles that were driving across shoreline areas that were exposed when the lake's water level was lowered prior to removing the dam. This is the north bay of Violin Lake. Portions of the bay had been filled with soil to create a log landing and to stage supplies when building the siphon between Violin Lake and the Cambridge Creek Reservoir. We used the filled area along the north bay of the lake to stage the wood and the rock that we needed for restoring Goodeve Creek, the wetlands, and the shoreline. The muddy areas exposed when the dam was removed and the water levels receded had become a playground for dirt bikes. The motor vehicles were crushing frogs and toads. We used excavators to build a series of shallow water wetlands on the level areas that were exposed after the dam was removed. This dry ground would never again be inundated by Violin Lake. The elevation of the dry ground was higher than that of Goodeve Creek, which was the outlet for Violin Lake. The orange wire flags mark the perimeter of the wetlands we were building by using the groundwater technique. The wetlands were dug deeper than the elevation of water in the restored Violin Lake. The basins filled with groundwater as they were being built. The soil removed from excavating the basins was placed on higher ground that was open and not growing trees. Excavator operators used logs to keep from getting stuck in the saturated soil. We used a laser level to take elevations to help guide the excavator operators in how deep to dig. A variety of wetlands were built in the dry areas of the basin. Logs and snags were placed to provide birds with perches and places for frogs and toads to hide. The soil that was removed from building the wetlands was spread loosely with pits and mounds to increase plant diversity. The compacted soil on higher ground was prepared for planting using the rough and loosen technique and then covered with woody debris to discourage motor vehicles from driving off the road. The rough and loosen technique really works. These goldenrods, cottonwood trees, and willows naturally germinated on the loosened soil less than 2 years after construction. Our next action involved disabling the siphon pipe that moved water from Violin Lake into Cambridge Creek and then into the Cambridge Creek Reservoir. Here's the building we call the valve house. The excavator is digging out soil so we can find where the siphon pipe from Violin Lake enters the valve house. The red arrow shows where the siphon pipe enters the valve house deep in the ground. The siphon pipe that is surrounded by groundwater at the bottom of the hole is marked by the red arrow. We removed long sections of the pipe so the siphon could no longer be used to drain water from Violin Lake into Cambridge Creek. Soil was placed in the bottom of the hole and compacted to prevent water from entering the pipes that were left in the ground. The excavator collapses and buries the concrete block valve house into the hole. The concrete blocks are clean fill, much like rocks. We worked to naturalize sections of the siphon trench that were bordered by grasses and non-native plants. We did not reshape sections of the trench where large trees were growing on the soil that had been piled years ago. The excavator has started the process of modifying a section of the trench so it looks more like a wetland. The operator is traveling over the soil that was piled when the trench was dug. Non-native plants are being removed and the surface of the ground is being leveled before we begin making bays, points, and gradual slopes. The excavator operator is making a peninsula and a bay by moving soil from the pile into the water-filled trench. The rocks that were saved will be placed in the water to provide basking sites and places for frogs and toads to hide from predators. The ditch with its steep banks and uniform depth was poor habitat for animals and for plants. The excavator is reshaping the trench to improve the quality of habitat for plants and for animals. You're looking at a section of the siphon trench that was reshaped 1 year after construction. It now appears and functions like a natural wetland. Here's how this section of naturalized siphon trench appears 2 years after construction. This straight trench was changed into a wetland with points and shallow water bays. You're looking at a side channel that was shaped to appear like it was dug by a beaver. This bay will fill with shallow and warm water in the spring that will be ideal for western toad breeding. The mounds, bays, and channels you see were not drawn on engineering plans before construction. The renovations you see were done at a low cost because we were on site full-time working in partnership with the heavy equipment operators while paying Sublattice Environmental by the hour for their work. I think you'll agree that this section of siphon trench looks more like a wetland. There will be many places for amphibians and small mammals to find food and to hide in their new home. Beavers had built dams across the siphon trench. We left these in place. Some water continued to flow from the outlet of the siphon pipe after the siphon was disconnected and the valve house was removed. The excavator exposed the siphon pipe uphill from the outlet. We cut and cleaned the inside of the pipe. We used a commercial plug to seal the end of the pipe. We used a GPS to record the exact location of the plug so we could inspect it for leaks at a later date. We then carefully filled the hole with soil. Removing the entire siphon pipe would have been a massive job involving draining water over 2 meters deep from a wide trench that was 880 meters long and cutting hundreds of trees that were over 100 years old. I'd like to show how the Violin Lake Restoration Project looked on August 12, 2023, almost 2 years after the project was completed. This is where Goodeve Creek begins, where the inside toe of the dam had been removed. Grass is growing on the restored floodplain of Goodeve Creek. Here is where the restored Goodeve Creek flows over the buried vertical grade control structure that was made from rock. The water level in Violin Lake is now the same as before the dam was built over 100 years ago. This is the southern bay of Violin Lake where we excavated wetlands in the basin and reshaped the shoreline over the old road. This is the restored shoreline where soil from the dam was spread over the old road. This beautiful shoreline wetland was built using the excavator only 2 years ago. Here's a shallow water bay we built along the edge of the lake. I really like how this restored shoreline appears with a shallow water wetland and pieces of wood that look like they washed up on shore. This restored ephemeral wetland should provide western toads with breeding habitat when it fills in the spring. The leveled and compacted staging ground on the north side of Violin Lake is growing a diversity of plants, and the best part is people are not driving in this area. Sedges and rushes are growing in the restored shoreline areas. A diversity of plants are growing where compacted soils were loosened. This seasonally inundated bay has become a wet meadow wetland. These wetlands were built in the dry North Bay of Violin Lake. This wetland was purposely connected with Violin Lake. This wetland was built where soil had been removed years ago. The snag was placed by the excavator operator who built this wetland. The straight and narrow siphon trench has been transformed into a series of naturally appearing and functioning wetlands. The wetlands that were restored in areas that had dried when the dam was removed greatly added habitat for birds, amphibians, reptiles, and mammals. These wetlands were restored without the use of dams, berms, pipes, diversions, water control structures, or pumps that are artificial and require maintenance. The actions taken to prevent motor vehicle damage to sensitive shoreline habitats were very successful. Restoring natural wetlands and streams provides benefits for climate adaptation and resilience by mitigating flood risk, extreme temperatures and drought, and by buffering high and low flows. I want to sincerely thank Robin Anchild for her extraordinary dedication and tireless work that made the Cambridge Creek and the Violin Lake ecosystem restoration projects possible. Her vision, leadership, and management skills are truly exceptional and, in my experience, unparalleled in Canada. Yes, it's entirely possible to restore a lake. The dams that were built years ago can be removed, and the wetlands can be restored to improve habitat for fish and wildlife. Well, if you like this video, let us know. Press that subscribe button so you won't miss any future episodes, and I wish you every success restoring lakes, wetlands, and streams where you live.